Good?
No,
It was fine. Okay. Okay. Welcome. And so today we have 2 hours where we are going to talk about sub-universal models of quantum computation or quantum supremacy models. So I would like to start by telling you why these models are important and interesting. Because, so you have heard, everybody now has heard about like Shor algorithm. Let's say, if we start, let's speak about the idea that quantum computers are predicted to outperform classical computers for computational problem. What does it mean? So there were first pioneering intuition and ideas by Feynman. It was not the first one, actually. There was a Russian physicist who had this idea before. But let's say there was this stream of ideas. Then there has been Shor algorithm, where indeed you can solve in a polynomial time a problem that we know takes an exponential time for the best non-classical algorithm. But this is not, if you want really to prove if the quantum computers cannot perform classical devices for computation, then Shor algorithm is not super satisfactory now for 2 reasons. First, because in order to challenge really the computational factoring with classical computers, it would require a number of qubits that today with the need for having fault-tolerant computation is totally out of reach. It's millions of qubits, so we cannot hope to do this today. And the second reason is that even if we would have an experimental demonstration of Shor with 1 million fault-tolerant qubits factoring a super large number, there is not a mathematical proof that tell us that we will never find a better classical algorithm for factoring that would allow factoring in polynomial time. So then in this sense, even Shor, even if it is very impressive and conceptually interesting, is not the best to really disprove the extended Church-Turing thesis. I'm going to talk about it. Anyway, to say that yes, quantum mechanics allows for building a computational model that allows to outperform classical capabilities. So then there is the need to find this kind of problems that we really can prove mathematically that yes, they can be solved efficiently on a quantum computer, and no, they cannot be solved efficiently on a classical computer, and this is the goal of this type of problems. So then I've already mentioned this extended Church-Turing thesis. So in the context of these quantum supremacy models, there has been a famous trilemma that has been put forward by Scott Aronson. It's called the Shor trilemma. And the idea is the following. So for us, we kind of believe, all of us, we expect that the quantum computers will outperform classical ones. But computer scientists, classical computer scientists, until we have somebody that might confirm this, until not so long ago, they were kind of believing in a thesis that is called the extended Church-Turing thesis, that says, extended Church-Turing thesis, that says that any reasonable model of computation can be mimicked efficiently by a classical Turing machine. So what is the grade of belief of this affirmation? Now, nobody anymore. We are not sure. So it used to be widely believed. Now with quantum even computer scientists start to not believe it so much. But then, so there are now three statements that cannot be all true simultaneously because of Shor algorithm. One is the extended Church-Turing thesis. The second is that we cannot factor classical number efficient. We cannot factor integer numbers efficiently on a classical computer. And the third one is that, yes, we can build a quantum computer that is able eventually to perform short algorithms. And so basically it is clear that these three statements cannot be valid in the same time. One of them must be false, and the aim of these quantum supremacy models is to prove false the extended Church-Turing thesis and prove that there is an exponential separation in the solution of certain problems. So what are these problems? So another feature of these problems is that typically they are sampling problems, where the problem is to sample out of a probability distribution that is a little bit ad hoc. So typically one consider a quantum circuit C, applied on an input state, for instance, the vacuum, and then we measure, for instance, in the computational basis, and then we get a string that is of bits of length n, and then we have this probability of x that is then given by the amplitude of our circuit on the initial state modulo square. And then what these models aim at proving is that sampling out of this probability distribution cannot be done efficiently, so in polynomial time, by classical computers unless some widely conjecture in computer science doesn't hold. So this is the typical reasoning. And then it is kind of obvious that the quantum device, the quantum circuit C, can instead produce samples efficiently, because we usually require that, always, we require that in the definition of these circuits we have a polynomial number of gates in the number of the bits. So then this is efficient, and then we just use it to do measurements. And so it's kind of built in to be efficient in a quantum setting. And so there are a list of candidates models, and people have been introducing a lot of them. So one of the most important, let me take a historical picture. So historical picture, the first is not boson sampling, but it's a proposal by Barbara Terral and David Di Vincenzo. And I've put the reference, it's a 2008, and the paper is called Adaptive Quantum Computation, Concept that the Quantum Circuits and Arthur Merlin Games. I'm not going to write the title, but this was the first model, and it was about certain Hamiltonians, especially, so it was less in the language of a quantum circuit. Then there has been boson sampling. And one of the reasons why this became famous, there are two reasons. One is that Scott Aronson is an excellent communicator and he has the blog and so on. The other is that the complexity conjectures on which it relies are stronger than this one. So it's even more plausible, the hardness of this than this one in this sense. Then there is IQP for instantaneous quantum polytime. This we're going to talk today. And then there is random circuit sampling. And then this is, for instance, what has been the object of the Google experiment. And today we are going to talk especially about these two. And we start with IQP. And so in the remaining of this hour, we talk about IQP, and we do, in principle, the proof of computational hardness, at least the simplest one that can be done. And then in the second hour, we talk about boson sampling. Okay, so then let's start with the IQP model. So IQP stands for Instantaneous Quantum Polytime, and it's called like this because let's write what the circuit is. So we start from plus states everywhere, and then here we have a circuit that is composed of gates that are diagonal in Z. And then here we measure X. So because these gates are all diagonal in Z, they commute with each other, so it doesn't really matter the order in which you apply them, and in particular you could apply them all simultaneously. That's why it is called instantaneous.
But it's only 2 qubit gate? Like it's only CC, not CC gate?
No, it's CC gate. There is also, you can also define it with control Z actually. There are different definitions of the gates in the model, and I'm going to focus here on something that, so the definition that is not even written in the notes, but it's the simplest that we can think about. That is Z, T, that as you know is this pi over 4, and control Z. And it is, so this also makes you understand why it is called sub-universal, because this is not a universal gate set, because it's so diagonal in Z, so you cannot get a universal gate set with only Z operation. What is missing here to have a universal set will be the Hadamard transformation. If you are the Hadamard, then you get universality. So then what does this circuit do? We just want to measure and get the samples that correspond to this bit string, and we want to prove that this task is hard to perform for a classical computer. One other thing that I forgot to tell is that typically these models, as you can imagine, they don't solve any useful problem. It's just about sampling. Then people are doing more and more effort to map the output probability distribution of these problems into something that is useful in some sense. For instance, boson sampling has been mapped into, it has been used as a useful random number generator for cryptographic applications, or this one has been linked to Ising model and computing the partition function of Ising model. I think for those who were there at the Jens Eisert talk at the Linné colloquium, he was also mentioning the mapping of IQP and Ising models. But typically, is not, they are not born to solve useful problems. Okay. So let's talk about the easiest possible proof of computational hardness. How does it go? So in the simplest possible version, we talk about the hardness of the exact circuit. So it's something that really looks like this. And if in your experiment you have gate fidelities of 0.99%, you cannot say anything about what you can build in the experiment, because it's only about the hardness of this exact model, how we see it. Proving the approximate version, where you tolerate a little bit of noise, it's possible, but it's much more technical. And the other thing that this proof that we address is going to be about, it's about worst case. So let me write off. So except the sampling, so no errors, and then worst case. It means that with the proof that we see today, what we prove is that the IQP circuits are not contained in BPP, which would be the class of problems that you can solve efficiently with a classical computer and a random number generator. So your MacBook. So then 2 comments. There are better proof, even in the original paper, no, not in the original paper, but in later papers, where they refine the proof with an average case statement. So the point is that here in the worst case, you just prove that it is not true that the full family of IQP circuits defined like this can be efficiently simulated, but you don't know which one are not. So then the situation, it's typically, it could be something like this, but you don't know which circuits are hard to sample. So if you want to do an experiment, it's complicated. In an average case scenario, what you prove is that if you take random instances of these circuits, then with a high probability, in the sense of some measure, for instance, if it was a unitary, typically people would sample with a hard measure, then with a very high probability, the circuit that you get is hard to sample. Of course, this is much better, but we're not talking about it because it's much more technical. So let's focus on this worst case scenario. We want to disprove this. So how does the proof work? Also, let's comment. I'm going to be a physicist and be not rigorous in a computer science sense. I'm going to mix up decision problems with sampling. They are clearly not, even this thing, I will not really be allowed to write it like this because BPP is a decision, is a class of complexity class for decision problems, and IQP is a sampling model. So we are mixing a bit apples and oranges, but it's to fix the ideas, it's much simpler. It avoids technicalities, and it's not too much wrong. But we have somebody that can correct us if we go too bad. So how does it work? This we are going to proceed ad absurdum. So we are going to suppose that IQP is efficiently simulatable, classically. Then this means that BPP contains IQP. So we are assuming this now. And then you know that you have seen with Anton, I believe, that you can also consider post-selection. So in particular, you could say, okay, now I'm going to only take the runs of this experiment where I decide that one qubit must, a flag qubit that I decide, let's say the first one, I must find it in plus. Then otherwise I discard the result. And this you can also do when you run a classical simulation. You can also decide that some string, some bit string, they must be plus, and then you can discard the rest. And this typically, so this amounts to define the class post-BPP and post-IQP. And this is much more powerful. So then the other part of the proof is to show that post-IQP is equal to post-BQP. In practice, what does it mean? First, so what BQP, you know, that is the class of problems that can be solved efficiently by a quantum computer. So we need here for BQP universal gate set. We cannot reach all the BQP computations with sub-universal gates. But then what happens? That if we add the post-selection, what we have to show is that we recover universality. So now I need to erase the first part of the blackboard because we are going to prove this. And then we are going to come back there to conclude. so I will not erase the rightmost part.
Julia,
Yeah,
could you please explain once the post IQP?
yeah, we are going to do it now.
Okay.
It's IQP with post-selection.
I mean, I'm just forgetting what post BPP was actually.
BPP with a post-selection. So you can discard all the runs that where a qubit flag bit or qubit is not in the state that you decide. So then it gives much more power because you basically you can you authorize to have more run in some sense until you get the flag bit or qubit in the state that you want.
Yeah.
Even if that has an exponentially low probability to happen, it's still compatible with the definition of BPP or BQP, and post BPP or post BQP. And there is a very nice note on that in the blog of Scott Aronson, because this thing of the possibly exponentially low probability at the level of post-selection in the definition of the class BQP, post BQP and post BPP was not in his original paper, and he figured out later that yes, this is compatible. So I think I put the references to this in the notes. But let's see, concretely speaking, what happens. IQP with post-selection. So what we want to show is that it becomes universal. So, and this is kind of simple. It's what we said that what we miss is the Hadamard transformation. So we can draw what is called the Hadamard gadget. So we take some structure that exists in this family of circuit, so namely some ancillary plus state, and then here we have the CZ, and here we have measurement in X. So we take one of these sub-blocks of the circuit, say, I don't know, it could be some line here, where this is a CZ with the input state, for instance. So at some point, we will have this control Z, this gate plus, and here we want to measure X. So we want to know what happens in this other mode. So we can do it. Let's do it explicitly. Let's suppose that alpha 0 plus beta 1 is a general qubit state of this this line, which could be a certain step of the circuit, and then so the input state is then psi 1, and is alpha 0 plus beta 1, 0 plus 1. And okay, let's forget about the square root of 2. So then if we write this explicitly, then this is alpha 0, 0 plus alpha 0, 1 plus beta 1, 0 plus beta 1, 1. And then we have the CZ gate. So we obtain the state psi 2, that is alpha 0, 0 plus beta 0, 1, alpha 0, 1 plus beta 1, 0 minus beta 1, 1. And then we measure X. So we have to make explicit here that we have either plus or minus state in the first qubit, because we want to discover what happens on the second one. So let's rewrite this to isolate the plus qubit. So this writes like alpha 0 that multiplies 0 plus 1 plus beta 1 that multiplies 0 minus 1. Then this writes like alpha plus minus 0 plus 1 plus beta 0 plus minus 0 minus 1. Then this we can rewrite in the final form. I hope it's visible, or maybe I should go on the other side. So if I take plus, then I should take alpha that multiplies 0 plus 1 and then I should take plus beta that multiplies 0 minus 1. Sorry, minus, wait, I'm confused. Beta that multiplies 0 minus 1. And then we have plus minus. That multiplies either alpha 0 plus 1 or minus beta 0 minus 1. Okay. So then you see that if the measurement outcomes, let's say that you can get either m equal to 0 or m equal to 1, if plus and if minus. So if if m equal to 0, we get alpha. Did I write it correctly? Does it make any sense? Yes.
Well, there are some parentheses missing. Like there's a closing one on the upper row
Here.
and a starting one after the alpha.
Just add in
A starting one after the alpha.
On the second row.
Here. Yeah, okay, perfect. Okay. So yes, if you measure 0, basically we obtain alpha 0 plus 1 plus beta 0 minus 1. Ah, yes, it works. So then this is, wasn't it, by the way, yes, sorry, wasn't it, okay, that's fine, because look, what is this? This is alpha plus beta minus, and this is precisely h psi, because our psi was alpha 0 plus beta 1, so if you apply the Hadamard, you get alpha plus beta minus. So then this is precisely the Hadamard. If m is equal to 1, instead we get alpha 0 plus 1 minus beta 0 minus 1, and this is equal to x h psi, because you get alpha plus beta minus, but there is a minus sign that you can get with a flip with x, because x minus is equal to minus minus. So basically, it's a little bit like the MBQC that you saw with Anton. You can write this like xm h psi. So if you want to use this gadget to apply a Hadamard, this is to be interpreted as an undesired byproduct operator, but you see that if you post-select on m equal to 0, it means that you only keep the outcomes where this flag qubit is in plus, then you recover the Hadamard. So yes.
Can you also write that as xz psi?
H z, yes,
Sorry.
because x h is equal to
Then-
z. Yeah, you can.
In that case, then there's no undesirable.
Yes,
stuff,
because
right?
z, it's if I write
Every gate is diagonal z.
then the Z is undesirable.
You're measuring
Oh,
namespaces.
yeah, I see, okay, yeah.
How did we get the plus to begin with if we didn't have a header mark before doing this procedure?
You do have it in the input.
Okay, right.
So it's just that I didn't write an explicit shape of the circuit, but suppose that you have, and this is really a bit out of reach, but suppose that you have, to make an example, I don't know, here you have CZ, then you have a T, and then you have a CZ of this with this. So suppose that you want to mimic a computation where you have at a certain point you need X operation, so you need a Hadamard, and then you can always find I don't know, suppose that you need it here, then there is always, in this family of circuits, there is also always one circuit that will have a line and a CZ where you need it. They all belong to this family anyway. So then the statement is that for any computation in post BQP, you can find a drawing of a circuit that belongs to the IQP class, that when augmented with post-selection and flagging certain qubits, gives you the same computation in post BQP. So this is roughly what we needed to show, that the post IQP is equal to post BQP. Now if we go back here, so this we have proven, and then what are the implications? Is that, remember, if we start with our ad absurdum hypothesis that BPP contains IQP, so IQP is simulatable, and then in particular with post-selection post-BPP contains post-BQP. Now this would mean that the post-BPP contains post-BQP, because I combine these two. But then this one has been shown to be equal to PP by Aronson, and there is also something that's called the Toga theorem, that says that PP is as hard as the full polynomial hierarchy. And here again I have to put almost, because there is again some technicalities and oracles and other things. But in spirit, PP is as hard as the full polynomial hierarchy. While instead post BPP is known to be contained in the third level of the polynomial hierarchy. Then if you combine the leftmost part with the rightmost part, you get that basically the third level contains the full polynomial hierarchy, and this is the so-called collapse of the polynomial hierarchy to the third level. I think you have seen with Anton the polynomial hierarchy. Yes? So it's a little bit like P and NP. We don't believe that P is contained. We don't believe that P is equal to NP, and we don't believe that all the levels of the polynomial hierarchy are contained one in the other. We believe that. We believe that they are strictly contained. We don't believe that they are all equal. That's a powerful conjecture. So then you say, okay, that's wrong. I don't believe it. Then it means that the original assumption was wrong, and that it must not be true that IQP circuits are contained in BPP, so it must not be true that IQP is efficiently classically simulatable. This is the idea of the first proof structure in the original paper. And as I said, is this kind of worst case, so it has been improved to the average case, and it has been improved to the case where we speak not only about the exact probability distribution, but to a probability distribution that is away in the total variation of this distance by a certain amount epsilon. It means that if you sample from a distribution that instead of being this one, is this one, that the difference between the two for each eye is bounded, then it's still okay. Which is a good news for experiments. Unfortunately, this has been studied much more for boson sampling, and for boson sampling there is such a result, but there is super many papers that shows that if you have losses, you go out of this very, very easily, and then you lose the hardness of the model basically. And with this it has been studied much less, I have to say. But this is in spirit, is a circuit kind of structure that really looks very similar to Google, what they did. So the gate fidelities for these models are already sufficiently good. I don't remember why they decided to do random circuit sampling instead of this one. I read something by Scott Aronson, but this could have been also done by Google. Yeah.
But to calculate like the output amplitude of this circuit on a classical computer, that shouldn't be too hard, right? Because the depth of the circuit is only one, so to say a number of 2 qubit gates. So it feels like they should be able to calculate a very large circuit on a laptop.
You cannot sample from it.
So this is probably what confused me in the Jens Eisert talk as well. Like, so even if I know the amplitudes of each state, you can't sample from it efficiently, or?
No, it's two different things. Because it's two very, I think I have the answer for this. I think it's two different problems to compute the amplitude of a specific outcome.
It's easy.
It's easy because it's one outcome. And this, it's called, estimation of an outcome. But to sample out of this, it means that you are exploring all the distribution, you need all the moments, and you're exploring a very, very large inverse space. So then it's about all the outcomes, and it's because all of these probability distribution that are hard, they always anti-concentrate. It means that they are always spread among all the possible outcomes, quite in a sort of, not flat, otherwise it would not be hard, of course, but kind of even way in the order of magnitudes. So it means that in every sample that you draw, you have a kind of almost comparable this probability that comes from all the outcomes. So then it's about sampling, it's about the full size of the inverse space, while estimating one outcome.
Okay, I see. So yeah, okay. So you really limit as how many states can I keep in my memory?
Yeah.
Like, it's not really about processing power. Like, because the circuit is only one depth. Like, the depth is very, very small. So I think, yeah, I guess it's how many amplitudes can I keep in memory then?
You do have entanglement, yeah.
Yes, but there's only one. Like, there's only one CC per pair of qubits, and I can push all the single qubits.
No, you can have a lot of CZ.
But since
You can have as many as you want here.
sure, but all gates in this gate set commutes, right?
Yeah.
So that means that I can push all CCs to the beginning, and if I have it even,
Yeah.
they cancel each other, so I just remove them completely.
Yeah, it's
So it
true.
only matters if there are even or odd numbers.
Yeah. By the way, what you say, it's true, and it means that you can also map this. If you do that, what you said, if you map all the CZ in the beginning, what do you get? Tell me. If you have plus a state and CZ, what doesn't it ring a bell? Huh?
Cat state, essentially.
All the think about one month ago. If you have plus states everywhere, and the CZ among the
Yeah, you get a measurement based quantum computing.
yeah with zero adaptivity though, because here you don't have adaptivity. So this also you got a cluster state, you know. Like if you got all the CZ in the beginning, which you can, then you interpret in that case the first part of the circuit as a cluster state, and then the rest is a measurement-based computation with zero non-adaptivity. So what you get, you get.
Yeah, you don't do any post election
You don't do
or
any feed forward.
yeah.
Then it means that measurement-based quantum computation with no adaptivity, so one round of it is hard to sample. It's not a deterministic computation, but it's hard to sample. Okay, maybe it's a good moment for a break. Yeah, it's the perfect moment for the break.